So good morning, everyone. Good morning, Dr. Arnab.
Yes, sir. I'm just stating your view. So, Professor Puneet Kumar Jain is currently working as an assistant professor in Department of Computer Science Engineering, NIT Rourkela, Odisha. Dr. Jain completed his PhD at Indian Institute of Technology, Jodhpur in 2018, an MTech degree from Delhi Technical University in 2011, and BTech degree from Engineering College, Bikaner in 2009. Dr. Jain has a research interest in AI for smart healthcare applications, where his research focuses on healthcare technology and algorithm development, aiming to advance patent patient diagnosis, assessment, and the treatment. He has published his research in the peer-reviewed and ACI Index International Journal and conferences. Very warm welcome to Professor Puneet Kumar Jain to our FDP cum STC Almis 2024. Good morning, sir.
Thank you, Arnab, for this generous introduction. And thank you for giving this opportunity to present my work with the audience.
Thank you, sir.
So I have shared my presentation. I think that is visible right now.
Prashanjit?
Is that visible? My screen is visible. I have shared the presentation.
Yes, sir,
Prashanjit,
it
you
is
are mute.
visible. It is
Yes.
visible, sir.
Okay.
Yes.
So if everything is ready, we may start the presentation then.
Yes, sure, sir. You can start.
Yes, sir.
Okay, great. Okay, before starting the presentation, let me tell all the audience that at any moment, if you have any doubt regarding the content or if you want to discuss in detail, you may raise your hand or you may ask your question or doubt while means doing unmute yourself. Means I will try to address the answer question in between. If it requires a separate discussion, we will do it offline. Okay. So let us start this presentation where I'm going to talk about machine learning applications for sustainable health infrastructure. Uh, Mostly, I'm going to discuss in this presentation on the role of artificial intelligence for cardiovascular systems. So we'll discuss the introduction about the role of AI in healthcare. We'll discuss the cardiovascular system, different kinds of modalities to analyze the cardiovascular functionality. Then we'll discuss certain methods to perform the pre-processing task because when we acquire the signals in out of clinic scenario, this is a critical step to perform to get an acceptable signal. And then we will discuss certain AI-based techniques, including the classical machine learning techniques and as well deep learning techniques. So if it has been communicated with you, this talk will be followed by a hands-on session where these methods will be shared with you, and you would be able to have an hands-on with these experiments with the publicly available dataset. So let us start with the introduction part. In the recent past, the application of artificial intelligence have been identified for various applications in medical domain. These are certain examples like classification of Alzheimer disease. So here we are using the MRI scans of brain. Then we are doing certain pre-processing, segmentation, feature extraction, and all to identify the Alzheimer disease. Again, there are various applications based on the MRI scans of brain or different organs. This is another application where we place the electrodes on the abdomen of fetus, of the maternal fetus. This is used to analyze the electrical activity of the fetus, and if there would be any abnormality, it has been identified that these kind of patterns can be extracted through these electrohistography patterns. Another application which was very popular at the time of COVID duration, by analyzing the X-ray images of the chest, detection of or diagnosis of the pneumonia. So since the COVID was causing the pneumonia kind of symptoms, people were trying to do this kind of task. Another aspect, many of you might have heard this term ECG, that stands for electrocardiography, that measures the electrical activity of the heart. So we'll discuss a little bit more about the ECG and various other aspects of the cardiovascular system. So I'm skipping right now here. This is another application where the mammogram images of the breast have been analyzed to detect the breast cancers. So this is also a very active research area where people are using various modalities to detect the breast cancers at an early stage. Again, this is one more area where people are trying to identify or trying to assess the structure of the bones in the radiograph images of the wrist. These wrist radiograph images provides an ample amount of information about assessment of the bone age, so that the maturity age can be predicted, as well as if there would be any abnormality in any particular any chemical profile of a particular person. This can be identified by the ratio of different parts of these bones. So means these applications are just a nutshell of the applications of AI in healthcare. There are n number of applications where AI has identified its role. And although means I would like to emphasize here is that right now in certain clinical applications, the AI applications, AI tools are being used, but in the future there are various AI tools which will be used in clinical. So now I will talk about the cardiovascular system now in detail. But before that, let us understand that our heart is a very important organ for the human body or any living cell, because heart supplies the nutrition and replenishes oxygen to each cell, and it works smartly throughout the whole life. When I'm saying smartly, that means whenever you want a support or a better support from the heart, it does dynamically, and at the relaxation stage, it get relaxed. Now we'll try to understand the functionality of the heart using these two diagrams. So in the left side, uh, the heart structure is describing that there are four important chambers, namely right atrium, right ventricle, and left ventricles. In the right figure, I have described the electrical conduction or this muscles related to electrical conduction of the heart. So means these are the two pictures of providing the insights of the heart structure from the two different aspects. Now, if we talk about the beginning of a cardiac cycle, although means cardiac cycle is a continuous process, so we cannot say which one is the beginning point. But let us say we are assuming that the beginning of one cardiac cycle is starting from
Sir, you have been muted.
uh, by which slide means I would cover.
Sir, for the last maybe 10 seconds.
Okay. So should I re okay, let me.
So again, you are muted, sir. So last time you have started from where we will beginning.
Sir, you got muted. Sir, you are still muted.
Yeah. I think I'm not sure if it is being done through the system or some guest or someone is doing that one. So okay, let me know if this issue happens again.
Sure, sir.
someone is muting me.
Okay, Dr. Arnab, can you look into it? Why is this happening?
I'm requesting please not to do any settings. Okay, so as all are the presenter, okay, we are having different participants with different institutes, so we are given a lot of access to the participants. Okay, so kindly need not to do anything, only listen. Anything happen, we will do that. Okay, this is my humble request, all of you. Okay, sir, please proceed, sir.
Okay. So let me re-summarize this presentation. I was discussing that there are two aspects of the heart describing in the left side of the figure and the right side of the figure. The left side of the figure is describing the physiological aspect of the internal structure of the heart, and the right side of the figure is describing the electrical conduction system of the heart. If you will observe the left side of the heart, there are four important chambers in the heart, namely right atrium, right ventricle, left ventricles. Uh, Although cardiac cycle is a continuous process, we are assuming that we are starting a cardiac cycle from the point where the blood enters into the right atrium from the superior vena cava and inferior vena cava. Please remember, this blood will be deoxygenated blood, right? And the oxygenated blood by the lungs will enter into left atrium, sorry. So let's assume that our cardiac cycle is beginning from this point. What will happen since the bloods have cations, right? So due to the entrance of the blood into the heart, these cations will enter into the heart, and an electrical impulse will be generated due to the change of this electrical impulse. Uh, the point where this electrical impulse will be originated is called a sinoatrial node. Now, the heart muscles have very important characteristic.
Sir, again you have been muted, sir. Sorry.
Yeah. Okay. So the heart muscles, when we apply electrical impulse on the heart, they contract. So as I have mentioned, that electrical impulse will be generated on sinoatrial node, and it will first traverse through atriums, simultaneously left and right atriums. So when it will traverse, what will happen? That left and right atriums will contract. If left and right atrium will contract, what will happen? The blood from right atriums will enter into left ventricle, and blood from left atrium will enter into respectively from atrium to ventricle it will enter. Okay, from right to right ventricle and left atrium to left ventricle. Okay, what we can do, Dr. Arnab, because I think someone is intentionally muting again and again.
Sir, you can continue your talk. In the meantime, I am actually taking the permission from the participant to be the presenter and changing it. In the meantime, you please continue. I am doing the changes.
Okay, okay. Otherwise, yeah, means what you can do is that to all the guests you may make them the audience, and only few as a presenter. So the presenter will have the rights.
Right, sir. Right, sir.
Yeah. Okay. So yeah. So after the atriums, the electrical impulse will traverse through the ventricles through these Purkinje fibers. If you will observe in the right part of this figure, there are Purkinje fibers. They act as an electrical conduction system of the heart. And again, as I have mentioned, when the electrical impulse will traverse through these okay. So if the ventricle will contract, what will happen if you will observe the structure of these walls? Uh, the tricuspid wall and mitral wall will close, right? Because the structure of this wall is such like that if the ventricle will try to push the blood, they will close and the pulmonary wall will open. Similarly, for the left ventricle, the aortic wall will open. So what will happen is that when the ventricles will contract, the deoxygenated blood from right ventricle will enter into lungs through the pulmonary artery, and the oxygenated blood from left ventricle will enter into body through aorta, right? And that's how one cardiac cycle gets complete. So if you will follow this particular dot, you will understand that how the blood flows through the body to the heart, to the lungs, and again to the body. So from right atrium, right ventricle, lungs, left atrium, left ventricle, aorta, then the body. I hope you get a little bit about how actually our heart works. So now we'll try to understand that what happens if there would be any kind of abnormality occurs with the heart. First of all, it's a very prominent kind of abnormality which occurs with the septum. Septum is the separating wall either to the ventricles, so it is called as ventricle septum, and there is another wall which separates atriums called as atrium septum. Uh, in normal case, this septum should not allow the blood from the left ventricle to ventricle or atrium to atrium. Although before birth, the septum between the atrium gets bypassed, and if you know that before birth, in fact, at the time of birth, this particular wall is open, and we use the lungs of the maternal only. Means the heart of the lungs of the fetus is not active at the time of birth, and after some time it gets active. This wall automatically get closed, and that's how the normal things work. However, due to some abnormality, this wall may not get closed properly. So this kind of defect is called as atrium septum defect or ventricle septum defect, depending on which particular wall it is occurring. Another kind of abnormality is that, as I mentioned, these walls should allow the blood flow in one direction properly. However, due to abnormality, when the ventricle get pushed, if they are allowing the blood into reverse direction also, this is called as regurgitation, right? So the regurgitation may occur with any particular wall, and accordingly they are called as mitral regurgitation, pulmonary regurgitation, tricuspid regurgitation, and so on. Another disease is that in normal situation, blood should flow properly through these walls. However, due to abnormality, if the walls does not open properly and the blood does not flow properly, this disease is called as stenosis. Again, the stenosis may occur with any particular wall, and it is called as pulmonary stenosis, tricuspid stenosis, aortic stenosis, and so on. This is also a particular heart disease, most commonly known as heart attack. The, biomedical name is myocardial infarction, in which in this particular disease, what happens is that due to the deposition of the plaque caused by atherosclerosis, the blood does not flow properly through the veins, which supplies the blood to the heart muscle itself. Due to that, what will happen is the heart muscle will start to die. And if the heart muscle will start to die, they will not function properly. And that's what we call heart attack. Now, analyzing the functionality of the heart, there are various modalities available. So we'll discuss a little bit about it. First one is the electrocardiography, where we place the electrodes on the chest to analyze the electrical activity of the heart through different angles. And that's why it is called as 12 lead system. Another modality is called as phonocardiography, where we use the stethoscope to listen the heart signals, heart sound signals. And if we record these heart sound signal and we plot them, the technique is called as phonocardiography. I hope you might everyone have gone through the screening through the stethoscope, sometimes through the medical person. Seismocardiography is another technique where a sensor called accelerometer is used to measure the vibration signals produced by the heart movement. Photoplethysmography means again many of might have gone through the testing through this particular device where uh, we use a device of coupled with the photodiode and photosensors. The objective of this device is to measure the variation of the blood through the veins, and since the blood amount through the veins will change with respect to the heart rate, we can analyze the heart rate as well as also sometimes a little bit indication about the blood pressure as well. Another modality is the echocardiography. Please excuse me. Another modality is the echocardiography, where we use the ultrasound techniques or various other imaging techniques to understand the internal structure of the heart. And this particular technique is considered as a gold standard technique because it provides more insights about the functionality of the heart. But the problem is these devices are bulky in nature and also costly. So that's why the availability of these devices are very limited. Therefore, if you would like to work on the systems which can be used at home or in the remote monitoring, probably we would like to incorporate the system which is low cost and user friendly. Considering these features, uh, uh, we started working on three devices: phonocardiography, seismocardiography, and electrocardiography. So I will now more talk about phonocardiography specifically because the cost and the user convenience to use the stethoscope is better compared to other devices. There is one more aspect why we focused on the phonocardiography is that although the phonocardiography and the electrocardiography may provide the diagnostic information related to any particular disease, phonocardiography is better to indicate the heart wall disease. Heart wall disease is one of the cardiovascular disease, and this is very critical considering the fact that there were 5 billion patients in US alone in 2009, and this number is increasing every year. More serious fact about this disease is that 50% of the heart wall disease did not timely diagnose due to the absence of symptoms. And if the symptoms will not diagnose timely, if the prevention will not take place timely, a patient is less likely to survive more than 2.6 years. Therefore, it becomes an important task to analyze the heart sound signals so that these heart-ward disease can be identified or diagnosed at an early stage. Now, why we assume that the heart sound signal analysis will provide early stage detection of the heart wall disease? The fact is, heart sound signals are generated due to the movement of heart walls, and therefore it is considered that any abnormality with the heart walls will be uh, manifested into heart sound signal much earlier. If you will observe, the first heart sound, named as S1 or also known as lub sound, is caused due to the closing of tricuspid and mitral valve. Second heart sound, S2, called as dub sound, is caused due to the closing of aortic valve and pulmonary valve. And therefore, if there would be any change in the characteristics of these valves, the time and frequency characteristics of these sounds S1, S2 may change. Thus, analyzing the time and frequency characteristics of these sounds will provide diagnostic information about the functionality of the heart wall. In addition to these sounds are called as fundamental heart sounds. So, in addition to the fundamental heart sounds, if there would be any abnormality like the regurgitation or the stenosis, Some extra sounds get present in the in between, right? Either in the systole period or diastole period. So, like mitral regurgitation, aortic stenosis will produce systolic murmurs. These extra sound are called as murmurs. So, by analyzing the time and frequency characteristics of the fundamental heart sounds and the murmur sound, if they are present, will provide ample diagnostic features regarding the heart valve disease. And that is the objective of our research work. So in this direction, we have proposed various solutions. I'm going to discuss few of them now. First one is a two-stage solution where our objective is to propose a solution for to detect the abnormality at the two stages. One is at the user end, and another is at the clinical end. At the user end, since the device is at the user, the objective of the algorithm is to detect just the abnormality instead of identifying or classifying any specific disease. Because even if the user know what is the particular disease, he has to communicate with the medical person for the proper treatment. So the fact is that user must should know or should be intimated as soon as possible about the abnormality so that he or she can contact with the medical person timely. At the clinical end, we are proposed to provide more detailed analysis to the medical persons and for the automatic diagnosis based on the feature extraction and disease classification steps. Now I will discuss little bit about the pre-processing step because that becomes crucial step when we intend to use or intend to monitor the heart functions in out of clinic scenario that is either at home or at office. We'll try to understand the impact of the noise on the heart signal through this figure. So you can analyze that first two cases belong to the pathological sounds due to the aortic stenosis and mitral stenosis. I will I will emphasize why we are considering these two cases here while we want to remove the noise. Rest three cases are describing the noise. This is the red noise, which is a synthetic noise added to the clean noise. This is the signal with the synthetic noise generated through the pink noise model. And this is the signal acquired in the real life scenario where there were noise components available. So you can observe that in different scenarios, the characteristics of the noise is different. Now let me clarify why we are focusing that these pathological sound. In the case of pathological sounds, we are considering these murmurs as a noise. Although these, as I mentioned, these murmurs provides diagnostic information. But first of all, we would like to identify the location of S1 and S2. Once we identify the location of S1 and S2, we can identify uh, the murmur is systolic murmur or diastolic murmur because if the murmur is systolic, we know that this murmur is specific to is belong to specific disease. If it is diastolic, accordingly there are certain categories. Therefore, it becomes important to detect the S1 and S2, and therefore we would like to remove the murmur as well. We want to emphasize S1, S2 so that we can identify systole period and diastole period. For this, let me discuss one approach based on discrete wavelet transform based denoising algorithm.
Sir,
Yes.
sir, could you please explain once again the last slide that
Uh,
regarding this different noises? The S2 and S1, they are normal, right? I mean, they will
yeah.
appear as normal.
Yes.
So, if you could please explain once again the first two kind of murmur.
Okay. Okay. Yeah. That's why I clearly emphasize because the fact is that if you remember when I was discussing the genesis of the heart sound, I have mentioned that S1 and S2 are called as are considered as normal heart sound and
Yes.
also called as fundamental heart sound. And if there would be any abnormality with the walls, some extra sound may be presented either in the systole period or diastole period. And these sound are called as murmur. Now, the murmurs provides diagnostic information, right? However, First of all, if we can identify where is the S1, where is the S2, then we can say that which period is systole period, which period is diastole period. Once we know that this is the systole, this is the diastole, we can say that is it a systolic murmur or diastolic murmur. So that's why in the first step, we would like to remove the murmur. We would like to identify the location of S1 and S2 only so that we can identify is it a systolic murmur or diastolic murmur. Once we identify that this is a systolic or diastolic, we can use the murmur information for further diagnosis. And that's why we want to remove the murmurs as well. Is it clear now?
Yeah. Clear. Thank you, sir.
So the fact is the murmurs are the biological signals, although they are pathological. While the rest of the three cases, these are the clean signals with the synthetic noise and the real life noise. Okay.
So,
So now,
sir, actually, sorry, sir, for the interruption.
yeah,
These
go ahead.
noises are, in general, they are filtered by appropriate filter, right? I mean,
Yes.
electronics filter to remove that.
Yeah.
Okay.
Yeah, so there are two approaches. Means if you are mentioning about the electronic filters, yes, you can construct the analog filters, electronic filters to perform the denoising. However, the means the cost of these analog filters or the electronic filters is little bit higher, right? Because you have to come up with the particular integrated IC, and you have to install this IC. You have to couple this IC with the sensor itself. While the technique we are going to discuss is called as digital processing, right? Once we recorded the signal, now we are doing the processing. Okay. So the technique I am discussing about is the digital processing, where once we have recorded the noise signal, we would like to denoise it. Okay.
Okay, sir.
Yeah. So this is a typical diagram of a DWT-based denoising algorithm, where it can be observed as a three-step process. First step is the decomposition, second step is the thresholding, and third step is the reconstruction. In the first step, the two filters, high pass filter and low pass filter, combinedly called as analysis filter, are applied on the PCG signal. As name is suggesting, high pass filter, it will pass the high frequency content available in the signal, and low pass filter will pass on only low frequency content. Uh, the output of these filters will be downsampled by a factor of 2, and that's how we get the detailed high pass filter output called as detailed level coefficient, and the output of low pass filter is called as approximation level coefficient. Once we get these coefficients, detailed and approximation level coefficient at level 1, we can perform the decomposition at a level 2. For that, what we do, we apply the same process on the approximation signal from the previous level. So we get the detail level coefficient at level 2 and the approximation level signal at next level. So we can decompose the signal up to a desired level. We'll discuss about that how we can identify the level of decomposition. Once we get these coefficients, the next step is the thresholding. Thresholding is nothing but to you can say the suppression of certain coefficients which are considered as a component of noise. We'll discuss in detail about how to estimate the threshold value, how to apply this threshold value. Once these coefficients get thresholded, we apply the reconstruction phase. In the reconstruction phase, again the two filters are applied, composed of high pass filter and low pass filter, and called as synthesis filter. Uh, in combination to the analysis filter, the synthesis filters are formed as quadrature mirror filter, right? There is a particular technique by which we can construct these four filters. So we construct the signals at a level 2, and then we apply the same process on the D1 and the obtain coefficients or level 2 to obtain the final signal. And we'll see that the final signal will be the D0 signal because we have applied the thresholding. I will discuss each of these steps in detail and we'll see the impact of these steps. First of all, the decomposition. So through this figure, you can observe that we were having this original signal with the sampling frequency 2 kilohertz. We decompose the signal up to 5 level using COIF5 as a mother wavelet. There are various mother wavelet families. We are using particular one due to the similarity of the characteristic of COIF5 with respect to the PCG signal. Now, you can observe that when we decompose a signal with 2 kilohertz sampling frequency, the frequency band of each level, right, detail level 1, 2, 3, 4, 5, and the approximation will be like this. Okay. Now, you can observe that the hertz sound signals are prominently available in detail level 4 and detail level 5. Therefore, what we did is that we only keep these two levels and we discarded other levels and we perform the thresholding on these two levels, detail level 4 and detail level 5. Right now, as I was saying that how you will identify that how many levels you should decompose, that depends on the frequency range of your desired signal. Like in this case, the frequency range of fundamental hertz sounds typically range from 20 to 120 kilohertz, right? And therefore, you can observe the level 4
Sir,
and level 5.
Sir, sorry,
Yes,
sir. Sir, sorry for the
we are
interruption.
unable
The
to
screen
see
is
the
not
PPT,
visible
sir.
anymore.
screen is not visible.
Yeah.
Let me check. But still, it is saying but the screen is being shared.
So not
Is it
visible.
visible?
No, sir.
So sometimes it happens due to, I think, technical error. If you reshare it, I think it will be visible again.
Okay, just.
Sir, kindly rejoin. I guess maybe MS Team network issue maybe.
Okay.
Yeah.
I think something is there. I think some issue is there with the.
Uh, sir, please leave and rejoin.
Can you remove me through the meeting? I'm not able to do that.
Oh, okay. Okay, I'm doing that. Okay, sir.
Let me do it through the.
I think now you are the presenter now. Can the participants see the slides?
No, sir. No, sir.
No, not yet.
Puneet sir, are you showing any slide?
Prasanjit sir, please remove me. I'm joining through the system. So I'm not sure what is the issue here. I'm not able to leave. In fact, I'm not able to leave or I'm not able to click any button on the MS Team.
Oh, okay, sir. Okay, sir.
Just a minute. Yeah, sir, am I audible?
Yes, sir, you are audible.
Yes, sir.
Yes, sir,
Okay,
you are audible.
Fine. Okay, I hope the screen is visible now.
Not yet,
Yes,
sir. Now
it is
okay, sir.
It is
visible.
Yeah, now
visible, sir.
visible. Yes.
Okay, fine. Thank you. Okay. Okay, so I think we have discussed this particular slide. Let us go through that. Yeah, we were discussing that one. So as I mentioned, it depends. First of all, you have to identify what is the desired range of your frequency content. So in this case, it was 20 to 120 kilohertz, and that's why the signal is falling in these two levels. So you should identify the desired frequency range for your desired component, and then you have to, yes.
Good morning. Sir, please carry on, sir.
Okay, okay. So once you have identified that, you can identify that in which particular range it is falling, and then you can proceed. Now, next is, as I mentioned, the next step is the application of the threshold, right? For that, you have to first estimate the threshold value. Although there are various popular threshold estimation methods like rigor sure, universal method named as square root loop, heuristic sure method, minimaxi method, and so on. However, all these methods do not incorporate any medical domain information here. Therefore, we come up with another idea to estimate the threshold value. The concept of the proposed threshold estimation method can be understood with this particular figure. In this figure, the signal at three different level of noise is described without a noise, with moderate noise, and with high noise. We calculate three statistical parameters: mean, median 75, and variance. Mean and variance are the classical statistical parameters, while median 75 is the 75th percentile value of shorter absolute value of the signal. That means in conventional median value, we calculate 50th percentile value. Here we are calculating 75th percentile value. Why it is so? Because if you will observe, the duration of S1 and S2, the summation of duration of S1 and S2 will remain less than 25% of one cardiac cycle. So we assume that whatever after this 25th percentage information, that indicates the level of noise, right? And that's why we calculate median 75. Now, yeah. So if you will observe in the case one where the level of noise is very low or there is no noise, median 75 is less than mean and variance both. In case of moderate noise, median 75 becomes greater than variance but remain less than mean. In case of highly noise, median 75 becomes greater than mean and variance both. Please observe, we calculate these statistical parameters on absolute of the signal, right? Although the signal is present is plotted as original one, but the statistical parameters are calculated on absolute values. So based on the relationship of these three statistical parameters at different SNR, we divide this into three cases. The case 1, case 2, and case 3 with respect to the relationship of median 75 with the mean and variance. And by analyzing the relationship of these three statistical parameters, we devised a new threshold estimation method with respect to every case. Once a threshold value is estimated, we have to apply this threshold estimate value according to a threshold function. Now again, there are two popular methods available to apply the estimated threshold value, called a soft threshold function and hard threshold function. However, there are certain shortcomings when we apply the threshold value using these two methods. To address that one, we come up with mid threshold function, and later at a later stage we come up with a non-linear mid threshold function. The mid threshold function uses two threshold values. These two threshold values are obtained using the estimated threshold value and the two parameters alpha and beta. These two parameters alpha and beta were optimized for the head sound signal using the genetic algorithm. And the value of alpha is obtained as 1 for all the cases, while the beta is obtained as 1.3 or 1.4 with respect to the median 75 less than equals to or greater than variance. Now, these are the certain qualitative results. First, this is the clean PCG signal. The second right is the noisy signal. This is the signal added with the synthetic wide Gaussian noise, where the SNR was minus 4.63 dB. Now we applied various threshold function methods, threshold estimation methods with a soft threshold function and hard threshold function. And at the end, we also applied the proposed threshold estimation method with the bid threshold function and proposed bid threshold function. And you can observe from this noisy signal, the proposed threshold estimation method is efficiently suppress the level of noise, right? These are more results applied on the signal contaminated with the pink noise and red noise, and you can observe that the proposed method was able to suppress all kind of noise efficiently. We also applied the proposed method on the signals contaminated with the real life noise, that means the signals acquired in the noisy scenarios. So you can observe at this particular point specifically, the proposed method is able to suppress the level of noise satisfactorily. And further, as I mentioned in the first step, we would like to remove the murmurs as well. We apply the proposed method on the pathological sounds as well. And you can observe that in most of the cases, the proposed method is able to suppress the murmurs. However, in certain cases, like in case of this aortic stenosis, pulmonary stenosis, the murmurs were not removed completely. This issue was due to the constant quality factor. I will talk about this particular characteristics of the wavelet transform in the coming slides. So therefore, we use another technique where we can tune this quality factor, right? And this is called as tunable quality wavelet transform. This is another method we proposed in this particular work. You may go through that. Let me just describe about the tunable quality wavelet transform and what is the difference between the discrete wavelet transform and TQWT. If you will if you will observe this particular figure, we are applying two steps here at the level 1. First of all, we are applying the two filters, high pass filter and low pass filter. And then we are applying the high pass scaling and low pass scaling, right? So it means these two steps are similar what we were doing in case of discrete wavelet transform. The difference between the wavelet transform and TQWT is that in case of wavelet transform, the frequency band was being divided into almost two halves, right? In case of high pass filter, the frequency band is from pi by 2 to pi and 0 to pi by 2, right? While in case of tunable quality wavelet transform, we can tune the frequency band of any particular level using the values of alpha and beta, right? Let me emphasize, please do not get confused with these alpha and beta parameters with what we use for the thresholding function, right? These are two different parameters. Okay. So the fact is what you should understand from this figure is that in case of discrete wavelet transform, we do not have the flexibility to change the frequency band at a particular level, right? While in case of tunable quality wavelet transform, we have the flexibility to change the frequency band at any particular level by modifying the values of alpha and beta, right? The values of alpha and beta can be calculated by these two equations, where the Q stands for quality factor and R stands for the redundancy factor. I'm not going to much detail about the impact of this Q and R. We may discuss if you are interested at the end. But this is the major difference between the wavelet transform and tunable quality wavelet transform. In case of wavelet transform, then we were applying the downsampling with the factor of 2. In case of tunable quality wavelet transform, we are applying the downsample by a factor of beta, right? Because we are dividing the frequency band with the factor of beta, and that's why we are doing it. Here we are dividing with the factor of 2. That's why we are downsampling with the factor of 2. Okay. Similarly for the low pass filter. Okay, and rest of the steps is same, right? To obtain the level 2 coefficients, we are going to apply the same steps on the approximation level coefficients obtained from the previous level. In this proposed method, we set the values of Q equals to 1, R equals to 8, so that the value of alpha and beta are obtained like this. And we decompose the signal up to 16 levels. As I mentioned, I'm not going into detail exactly how these the decomposition exactly take place through the TQWT. We may discuss, those who are interested, we may discuss after the presentation. Okay. Yeah, one thing is that once we decompose the signals into different levels, we can identify the center frequency and the bandwidth of any particular level using these two equations. Now, once we decompose the signal using tunable quality wavelet transform up to certain levels, so this particular figure is describing the original signal, one pathological sound signal, decomposed into 60 different levels. Now, our task was to identify the S1 and S2, right? So we want to identify a particular level, a particular subband, where the S1 and S2 are distinctly present, right? So that we can identify the location of S1 and S2. And if you will observe, the level 16 is have better distinct S1 and S2 compared to other levels, right? However, what happens is that, what is the challenge here? That in different pathological sounds, the frequency range of fundamental heart sounds vary. That means, in this particular case, the fundamental heart sounds are prominently present at the 16th level. In another pathological sound, it might be present in 14th level, or in another level, it might be present in, let's say, 11th level. So the another task is that how to identify a particular subband where the fundamental heart sounds are distinctively present. For this, we use a particular factor called Fano factor instead of kurtosis, as one being used in the literature methods. The impact of Fano factor can be understood in this particular example. This example is describing the two cases for the aortic regurgitation and aortic wall ejection. This is describing the obtained decomposed signal at two different levels. We are just describing them as L1 and L2 and their absolute signals. We calculate the kurtosis value and Fano factor for both the levels. Now, in case 1, if you will observe, the kurtosis value and Fano factor both are higher for level 2. And in level 2, the fundamental alert sound S1 and S2 are prominently present. That means both the parameters are selecting L2 where the fundamental alert sounds are present prominently. In case 2, the kurtosis value is higher for L1. Fano factor is higher for L2. That means if we will use the kurtosis value as a quality index or the parameter, L1 will be selected. If you will use the Fano factor, the L2 will be selected. And the L2 is the level where the fundamental alert sounds are prominently present compared to L1. That means the Fano factor provides better indication of presence of fundamental alert sounds. Once we selected one particular level, what we did is that we applied the thresholding method on the selected level using the same concept we discussed in the previous topic. So we calculate the threshold value, estimate the threshold value, and we applied the threshold value using the bit threshold function. Once we denoise the signal, we identify the location of S1 and S2 using an state-of-art method based on hidden semi-Markov model proposed by D.B. Springer and other. And once the location of S1 and S2 have been identified, we can identify the systole period and diastole period. And from these periods, we calculate the time domain features. I'm not going in nitty-gritty because these are common known time domain features related to the length of S1, S2, energy of S1, S2, systole period, diastole period, and so on. So various time domain features, including the ratios of the duration, Faro factor, kurtosis, zero crossing rate, sample entropy have been calculated. Then we calculate the frequency domain features. We divide the frequency bands into 4 bands, considering the impact of the heart sound signal and the pathological signals into different bands, and that's how we divide these 4 bands. And for each 4 bands, we calculate the energy and we calculate the energy of each particular bands and also the entropy. Once we calculated all these features, okay, I think that is okay. So the fact is that we also calculate the energy and entropy of each band obtained using the tunable quality wavelet transform. So we are using the tunable quality wavelet transform for 2 purposes. One is for denoising, and another is for the feature extraction. Once the features are extracted, we apply the classical machine learning techniques, including the support vector machine, k-nearest neighbor, where we consider various versions of the k-array. As I mentioned, this particular session will be followed by a hands-on session, and where whatever I'm explaining will be experimented with the publicly available data set. So you can try all these methods with your own. Then we also applied the various ensemble methods, including the booster trees, back trees, subspace canon, subspace discriminant analysis. For the results, we use a publicly available datasets where there are 5 categories available. Although for every category there were 200 samples. However, we discarded certain samples where there were 3 cardiac cycles were not present. So after the discarding, the number of samples for each categories are like this. These are the results obtained using the SVM, the various versions of SVM, linear SVM, quadratic SVM, cubic SVM, and the Gaussian SVM. You can observe that in most of the cases, the normal case was being identified with 100% accuracy. So this is the table describing the obtained results using the SVM quantitatively. And you can observe that the best results are being obtained through the quadratic SVM method. That means where SVM is being used with the quadratic basis function. These are the results with the Cannon method. Okay, I'm not going into much detail about these methods. I will just emphasize the conclusion of these numbers, and then I will conclude. Okay. Yeah, so the fact is that the best accuracy we obtained is the 99.04. This is through the subspace Cannon method, right? And the important thing you should observe is that with almost all the cases, we were able to classify the normal signal with other pathological signals with 100% accuracy, right? That means the normal versus abnormal detection rate was 100% for almost all the methods. It indicates that whatever the features we have extracted were significant to capture the pathological cases versus normal cases. Also, the overall accuracy is 99.04. That means other pathological cases were also being classified with a satisfactory performance. There were certain, we compare the results of the proposed method with the existing recent methods, and obtain, we observed that the proposed method produced the better results compared to all these methods. Now I will discuss we applied some deep learning approaches based on the CNN model and based on the CNN hybrid of the CNN and the GRU model. I will describe that how we have done this, and you will you will experiment with these models in the next hands-on session. In this approach, this is the block diagram of the proposed approach, where we first perform the few basic steps as the pre-processing. Then we decompose the signal as we have discussed up to 5 level using the COEF5 wavelet, mother wavelet. Then the obtained coefficients, excuse me. Okay. So once we decompose the signal up to 5 levels, the obtained coefficients are used as input to the CNN model. These are the pre-processing steps: uh, resampling, normalization, and resizing. Uh, Resampling, normalizations are the conventional steps. What we did in the case of resizing is that after observing the data set, we found that due to the variation in the heart rate, the duration of 3 cardiac cycle was varying significantly. But if we will extend this, we extend the features with the original signal, this variation will also get factored, right? So to avoid this particular aspect, we first resize the signal like such that all the silent period was removed, and then we make the length of each signal almost equal. After that, as I mentioned, we decompose the signal up to 5 levels. So that's how we get these 5 level coefficients. Although means in this particular figure, we are plotting the signals after reconstructing the signal at each particular level, right? For the input, we only consider the coefficients. We are not reconstructing the signal, okay? The, the coefficients were considered as input to the CNN. We considered very basic CNN model where we only constructed 2 convolution layers with very small size of filters. There were only 1 x 5 size filter with the 16 number of filters. In the second convolution layer, again, the size of the filter was 1 x 5 with just 8 filters. And at the end, we use a fully connected layer with the 5 neurons since there were 5 classes. And these are the obtained results. Or again, you can observe that even with the very small size of CNN, the accuracy obtained is close to 99%, right? And again, for the normal case, the accuracy is close to 100% accuracy, 99.16 F1 score we achieved. So I would like to conclude what we have discussed till now. What were the observations we observed from the obtained results and the methods. First of all, the algorithms to classify the heart sound signal based on the multi-domain features and machine learning techniques have been presented. Using the proposed method, the accuracy of 99% or more than that is achieved. And there were following results we observed for these satisfactory results. First of all, the use of tunable quality wavelet transform. As I mentioned, the tunable quality wavelet transform gives you the freedom to tune the quality factor of the wavelet, right? And with that, what you can do is that you can identify the frequency bandwidth of any particular band. So means the purpose is we want to discriminate the fundamental heart sounds with the murmur sounds, right? So that we can identify the S1, S2, and then we can do the further processing. So the use of tunable quality wavelet transform in the direction. Another thing is that the inclusion Am I audible?
Now you're audible.
Okay, I
But
think the
you,
net.
you please share your screen. Yes.
Yeah.
Mhm.
One minute. Let me share the slide. Yeah. Okay. Is my screen visible now?
Yes, it is visible, sir.
Okay. Okay. So, okay. So we were discussing about the conclusion part of the presentation. We discussed that there were certain reasons behind whatever the results we observed. One more thing is one important thing what we observed is that as I have mentioned, our objective was to do the two-stage classification or two-stage detection of the heart walls. At the user end, we only want to identify any abnormalities there or not, right? And this is the important thing because if the abnormality can be detected at an early stage, the user can be prompted for medical intervention at an early stage. And if we, means the whatever the methods we tried, we observed is that in all most of the cases, the accuracy for the abnormality detection was close to 100%, and that is very satisfactory for these kind of methods to perform the normality versus abnormality detection. However, I would like to focus one thing here is that in this particular data set, what we have experimented for this particular result, this data set does not contain any kind of noise. And that's why that might be the one reason most of the methods in the literature also our proposed method achieved a very high accuracy. But as I mentioned, when we have to experiment in the real life noise, the signal is vulnerable to be contaminated with various real life noise, and therefore such kind of system should be experimented with the signal contaminated with real life noise. So that is one particular issue with this. Another issue is that in this particular data set, very limited number of diseases are considered. There are only four particular diseases available. So means but the fact is, in case of phonocardiogram, in the publicly available data sets, I have that slide where okay, I will come to this particular future work again. But these are certain publicly available data sets where there is only one this particular data set with the five particular known categories, while other data set where the most popular data set is available through this PhysioNet 2016 challenge, but the categories are only normal versus abnormal. In 2022, although there is one more data set came into the picture, Sarkor data set, although it belongs to the pediatric heart signals, not the adult one. But yes, the experiments can be conducted on that particular data set in a better way. In addition to that, I would like to highlight certain points where the future work can be focused. One thing I have not discussed in detail is the exploration of the seismocardiograph signal. When I was discussing different modalities, I have mentioned that accelerometer can be used to measure the vibration signals from the chest, right? And that technique is called as seismocardiogram. Why that technique is very important? Because the size and weight of the accelerometer is very small and light, right? And therefore, it becomes very suitable for the wearable technology, right? And therefore, people are exploring the application of seismocardiogram for various purposes. Another aspect is the exploration of various time frequency domain, right? As we have discussed, tunable quality wavelet transform help us to improve the accuracy much. There are various other time frequency domain techniques available. We may experiment. We are experimenting those things. One more thing is that in this particular application, a quality index will help significantly. when I'm talking about the quality text, there was one application we have discussed that once we have multiple signals, which particular signal is having more quality, better quality. That is one objective. Another objective is that many times when we record the real life signal, it may happen that in certain part the impact of noise is very high. In another part, the impact of noise might be significantly low. So if we have certain quality factor or quality index which can identify a particular segment with low level of noise, that will improve the diagnostic accuracy of the system significantly. Another one is that what we are exploring right now is the use of heart sound signal for the identification of myocardial infarction. As I mentioned, myocardial infarction is the biomedical name for the heart attack. Uh, in conventional method, ECG is the more popular technique to identify the heart attack. But in the literature also, and we are also observing that heart sound signals may also provide diagnostic information related to the heart attack at an early stage. So this is another area where those who are interested to work in this can work. Those who want to start doing the research in this particular field, I have mentioned certain papers which are describing which are having certain review and also describing certain basic steps in detail. So I specifically picked these few papers here. I will share these slides with the organizers, and then the organizers may share these slides with all the participants. So by this, I would like to end this presentation, and I now open the session for the questions and answers.
So all the participants, have you any queries? So please let us know.
I think there is one hand raised, Tawfiq Ahmed. You may ask your doubt now. You may unmute yourself and you may ask your doubt.
Yeah, sir, this denoising using TQWT and different algorithms, these have been simulated using MATLAB, like programming, or any sort of simulating design is there available?
No, no. In the next hands-on session, you are going to do. If you are interested, you can do these experiments with the MATLAB. So,
Okay.
yeah. So we are going to do that. So all these things, whatever I have discussed in this presentation, specifically have all these experiments have been done through the MATLAB only.
Okay, okay, okay. So, sir, actually, I'm quite interested to work with these biomedical signals. So, in future, if I want to talk with you, then will I send an email to
Yeah,
this
I have
email ID?
mentioned. I would like to happy to address any query related to the research. Which I have already mentioned my mail ID at this particular slide, or you may contact with the organization to reach with me.
Okay, thank you, sir. Thank you. I will get back, sir. Thank you.
So,
Sir, one question, sir.
Yes, please.
Hello.
Yes, please. Please ask your question.
Hello.
Yes, please ask your question.
Sir, am I audible?
Yes, yes,
you're
please.
Yeah, sir. Can these algorithms and techniques be used for other disease detections also? Yeah, it is only for the cardiovascular section only.
No, okay. So whatever I have discussed is specifically for cardiovascular system, but it's not like that these techniques cannot be used for other techniques, right? Specifically wherever there are the signals are related to the sound signals, right? Like in case of if you are talking about the lung sounds, yes, the similar kind of techniques you can use. However, certain tunings will require, like for the threshold estimation, we use the median 75 because we have understood that the duration of S1 and S2 is 25%, less than 25%. So accordingly, there are certain decision points you have to take, like which mother wavelet would be more suitable for your application. how many decomposition levels you have to select, right? What will be the value of Q and R? So there are certain decision parameters you have to take corresponding to the application, but these techniques can be used for various applications.
Sir, could you please include certain latest research papers in this area? As you have mentioned 2018, 19, 20, some latest which we can take it as a base paper, or we can study and get more knowledge what can be done next for us.
Okay, okay. I will add certain recent papers which are based on the deep learning techniques and all, and then I will share these slides.
Okay. Thank you, sir. Thank you.
Sir, one more question. Is Kaggle helpful for this sort of sound related data? I mean,
Oh,
heart sound related data?
pardon?
Sir, there is one site actually, Kaggle, to get
Kaggle,
the
yeah.
data set. Yeah. So, does it provide the data related to the sound of hertz? I mean, the sound related data?
Uh, okay, so but the fact is that it generally it depends that through the Kaggle, whatever the data set we are getting, not only in this particular domain, in any particular domain, when we are getting the data set from the Kaggle, the authenticity is not established, right?
Yes, yes,
So
yes.
if many researchers are using that one and they are referring that one, then we may go through that. Otherwise, first of all, we have to identify what was the authenticate source. Similarly, whatever the data set I have mentioned, probably they might be available through the Kaggle also, but their origination was different, right? So first of all, you should try to identify who is the main originate of those data sets.
Okay, okay.
Right. If you will go through the recent papers, you will get to know that okay, what are the prominent data sets in that particular field.
Okay, sir. Okay, sir. It would be very helpful for us if you could please kindly share this PPT, this presentation with the organizer
Yeah,
team.
yeah, I will do that. I will do that.
Okay.
Shortly, I will do that. I will update a few recent papers as one of the participant requested. So after that, I will do that.
Thank you, sir. Thank you.
Any other question? And I will request all the participants that those who are interested to explore these kind of techniques, as I mentioned, there would be a hands-on session, and that hands-on session will cover all the techniques and the concepts we covered in this presentation. So, Mr. Pratyush, one of my PhD students, will try to explain all these concepts and the implementation of these methods through the MATLAB.
So MATLAB. Okay.
Yeah, MATLAB implementation will be required. Otherwise, you would not be able to experiment them.
Okay, sir. I hope there is no other queries from that participant. So, thank you, sir, for your very beautiful interactions. Okay, so hello.
Yes, yes, please.
Okay, so okay, sir. So now we are after 10 minutes again. We will start our hands-on session, sir. Okay, so in the meantime, okay, so we are announcing for that some short break. Okay, and